Welcome, I am Emanuele Vannacci and I present TRRespass, exploiting the many sides of target refresh. This talk is about RAMR, a memory issue that today seems to be solved because memory vendors are advertising RAMR-free memory devices. This thanks to the mitigation we call target refresh. But what target refresh is? Very little is known about its workings, since there is no standard and the memory vendors do not release any actual implementation detail. Today, I'm going to demystify some target refresh mechanism, showing that it is not the mitigation we thought, but target refresh is a more general term that identifies a whole class of mitigations. Indeed, we reverse engineer its design embedded directly inside the DRAM circuitry. Our analysis leads us to discover a new hammering pattern, the many-sided row hammer. Indeed, hammering a huge number of rows up to 20 allowed us to bypass the mitigation. We evaluated the effectiveness of target refresh on DIMMs from 3 of the major vendors, currently holding 95% of the DRAM market. What we figured out is that they are all selling vulnerable DIMMs. The current slide shows a CPU. Integrated with the CPU, we can find the memory controller. When the CPU needs to access memory, then the memory controller issues specific DRAM commands to the memory modules. The memory controller must ensure that DRAM commands respect timings constraints defined in the memory specifications. Indeed, DRAM is a synchronous technology, but besides being synchronous, it is also dynamic. It means that data must be refreshed periodically. Each bit of information must be refreshed every 64 milliseconds. We call this interval retention time. However, the memory controller issues a refresh command every 7.8 microseconds, and each refresh command refreshes only a small portion of the memory. We can represent memory as an array of cells organized in rows, and each cell represents a bit of information. When the memory controller wants to read data from a row, such a row must be copied in a buffer called row buffer. The memory controller first issues an activate command to bring the row data in the row buffer. The read operation then is performed directly on the row buffer. If the memory controller wants to read from another row, it must issue a precharge command to close the row, bringing back the data from the row buffer into the row. Then it can open the other row, for example in the figure, row 3. If an attacker repeats this sequence of commands, activating 2 rows fast enough within a refresh interval, likely it will get an error somewhere, a bit flip, and this is row hammer. In particular, in the slide, the double-sided variant is depicted. 2 aggressor rows surround a victim row in which the bit flip occurs. Fortunately, over the years, many row hammer mitigations have been proposed. Among those, some hardware mitigation are used in practice. The first hardware mitigation we can find in our systems make use of error-correcting codes. ECC solutions have been already investigated in previous work. Other solutions exploit refresh commands, since refreshing a row restores the cell's electric charge, and it prevents bit flips occurrence in such victim row. For example, some systems enable a double refresh frequency. However, such solutions have been widely investigated in the past, and it has been shown that it is not totally effective in mitigating row hammer. In this talk, we will focus our attention on the so-called target row refresh. TRR is an umbrella term that in practice is used to identify many different implementations. We refer to these mitigations as TRR-like mitigations. However, all these mitigations share a common idea. Victim rows must be refreshed to prevent flips, and to detect rows too frequently activated, row activations must be monitored. However, target refresh operations depend on the specific vendor designs, about which we don't have details because they are enforcing the security by obscurity principle. We could identify 2 main classes of implementations. The first one is called pseudo-target row refresh, and it is implemented in the memory controller. The second one is the in-DRAM target row refresh that, in contrast, is implemented in the DRAM circuitry, and it does not require any support by the memory controller. Pseudo-target row refresh was introduced in 2013 by Intel to protect DDR3 systems. It can be found even in the first generation of DDR4 modules. Our analysis on a sample of 42 DIMMs shows that in-DRAM TRR has been deployed only since 2016. Previous work has investigated the effectiveness of memory controller mitigations, and reports of bit flips on DDR4 devices have questioned the effectiveness of target refresh. Our work is the first one focusing on in-DRAM implementations of target refresh and on the last generation of DDR4 devices, built mainly after 2016. Indeed, we traced back one DIMM from our sample to 2015, and the other 41 DIMMs report manufacturing date after 2016. Our goal is to reverse engineer in-DRAM target refresh to shed a light on the actual implementations. We aim to evaluate the memory module security, and we tested our DIMMs against a novel hammering pattern that we dubbed the many-sided hammer. It is a completely new pattern that allows to bypass target refresh, hammering up to 20 rows that can be cherry-picked in a specific way. To automate memory testing without relying on reverse engineering techniques, we built TRRespass, the first row fuzzer able to automatically generate hammering patterns. Reverse engineering poses some challenges. Since the DRAM is synchronous and the mitigation is designed directly inside the circuitry, analysis from the CPU side is not feasible anymore, basically because we are missing side channels. For two reasons, we used the softMC infrastructure, providing us with an FPGA-based memory controller. The main advantage of using softMC is that we have full control on the DRAM commands the memory controller issues. For example, we can completely disable refresh operations. To study in DRAM mitigations, we tried to abstract from the single implementation, and we identified two components that target refresh design must include: the sampler and the inhibitor. So the sampler tracks the row activations and it keeps a set of rows that a hammer is targeting. Instead, the inhibitor prevents bit flips, selecting rows from the sampler set and, for example, refreshing victims. The first question we asked ourselves is how big the sampler is. So we figured out an experiment to carry out on one device. By softMC, we completely disabled any refresh operation in the background. In each test, we pick n aggressor rows and we perform a series of hammers. We issue 8,000 activations for each aggressor row. Then, with softMC, we issue a certain number R of refresh commands. We repeat this sequence of commands for 10 rounds, and then, after 10 rounds, we look for hammer bit flips. The following slides will show the result. Try to focus your attention only on the meaningful part I'm going to describe. In the figure, the x-axis reports the number of aggressor rows, while the y-axis reports the number of refreshes issued at the end of each hammering round. Each column shows tests for a different number n of aggressor rows. Each cell reports the number of bit flips triggered activating n aggressor rows and issuing R refreshes. Increasing n to 2, the third column already tells us something interesting. It can be noticed that introducing one refresh operation at the end of each round, the number of bit flips decreases from almost 3,000 to only 1. This leads us to the first observation, that is, the mitigation acts on every refresh command. Going on and increasing the number of aggressor rows even more, we start seeing something interesting again. Let's consider column 4, number of aggressors equal to 3. The number of bit flips decreases significantly when introducing up to 2 refreshes. However, it plateaus when the number of refresh operations is equal or greater than 3, without going down to 0. Notice that when hammering both 2 and 3 rows, the plateaus happen when R, the number of refresh operations, is equal to n, the number of aggressor rows. This leads us to the following additional observations. The mitigation can sample more than one aggressor per refresh interval, and it can refresh only a single victim within a refresh operation. But how can we recover the size of the sampler at this point? Simply by performing the same experiment for different number of aggressors n. While increasing n, we search for the scenario where the number of bit flips stabilize and R, the number of refreshes, is less than n, the number of aggressor rows. When this happens, we can conclude that we have overflowed the sampler size. So, varying n up to 9, we notice that, starting from the column associated with n equal to 4, the plateaus happens when introducing 4 refresh operations. at the end of each round. This leads us to conclude that the sampler size is 4, meaning that the sampler cannot track more than 4 rows. The last observation is that sweeping the number of refresh operations and the number of aggressor rows while hammering reveals the sampler size. To confirm this theory, we carry out a test on softMC, hammering a variable number of rows. We pick n aggressor rows and we perform a series of activations. Refresh commands are issued in such a way as to respect a refresh interval of 64 milliseconds, meaning that we issue a refresh command every 7.8 microseconds. The plot reports on the x-axis the number of aggressor rows we activate, while in the y-axis the number of bit flips we trigger. Hammering less than 5 rows, we cannot observe any bit flips. However, activating exactly 5 rows, we could trigger many bit flips. Hammering more than 5 aggressor rows, we observed a variable number of bit flips. Our hypothesis is that the sampler tracks rows based even on their address. Experimenting more with another device also, we could enforce this hypothesis, leading us to an additional observation. This observation is that the sampling mechanism is affected by the addresses of the aggressor rows. However, we have seen that overflowing the sampler size, it is possible to trigger bit flips by passing target row refresh. One main problem with this approach I just described is that it does not scale. It is not feasible to carry out a large-scale analysis in such a way. This is why we looked for a more scalable approach. We found it in one of the most promising techniques, fuzzing. Fuzzing has two main advantages. The first one is that we can ignore memory controller optimizations that, for example, reorder memory access to improve performance. The second one is that we can apply this approach in a black box fashion without reverse engineer the specific TRR implementation. Our fuzzer TRRespass is able to test memory modules through hammering patterns randomizing two parameters. The first principle we took into account is that the sampler can track a limited number of aggressor rows, and then the first parameter is the number of aggressors. The second principle we considered is that the sampler may be row address dependent, and so we fuzz also the aggressor locations. We evaluated our fuzzer on a consumer line machine. We bought 42 DIMMs from 3 of the measured vendors, Micron, Samsung, and Hynix. We tested all the modules singularly because even DIMMs of the same model may contain different DRAM chips. We have run TRRespass on each module for more than 6 hours, fuzzing the hammering patterns. Then we tested again 256 MB of memory for each module, against the best pattern, that is the one triggering more bit flips during the fuzzing stage. We could observe bit flips on 13 DIMMs out of 42. For each vulnerable DIMM, we could retrieve many effective hammering patterns. What is surprising is that in general, modules from 2 vendors require a huge number of rows, up to 20, to experiment bit flips. Moreover, as our machine allowed us to set the refresh interval from the BIOS, we experimented with a double refresh interval configuration, and we could still trigger bit flips. We confirmed that double refresh frequency is not a completely valid mitigation against a row hammer, even combined with target refresh. What can confirm is that fuzzing is an effective technique for memory testing. However, the fact that we could not trigger bit flips on some DIMMs does not mean that those DIMMs are not vulnerable. There is still room for improvement. For example, adding more parameters we did not consider into TRRespass. Or in general, getting flips could just simply require more time or to test more memory. Since the hammering patterns are so different from the previous standard ones, can bit flips still be exploited? Yes, but for example, the memory templating step in which we analyze memory to find flips at specific page offset must be anticipated by another step in which we scan memory to find the best pattern. One common requirement of RAM exploitation techniques is the availability of contiguous physical memory that can be allocated exploiting huge pages or side channels. We can still rely on these techniques as far as the hammering patterns fit into the allocated memory chunk, since they can now be very long, including many aggressor rows. However, we observed that the location of the aggressors is not always a strict constraint. We can pick the aggressors with some degree of freedom, not necessarily close to each other. The exploitation stage requires, of course, bit flips repeatability. Our experiments confirmed that bit flips are still repeatable, although hammering with a specific hammering pattern, spurious bit flips can be generated. However, a solution already exists, masking the row columns that are irrelevant. To prove the feasibility of previous techniques, we implemented the 3 example attacks. The first one is the original privilege escalation exploit. The second is the co-hosted virtual machine access via RSA corruption. And the third is the pseudo opcode flipping exploit. In conclusion, in our paper we have shown that target refresh fails in protecting modern systems from roamer attempts, because hammering with no standard variant, it is still possible to trigger flips. For example, we have shown that hammering up to 20 rows, we triggered flips on last generation DIMMs from 3 of the measured vendors. Our results proves that DDR4 devices are way more vulnerable than DDR3, since we could trigger flips with few activations. While DDR3 devices require 135,000 activations, we could trigger flips with less than 50,000 activations. We have shown that fuzzing can be used to test memories for rammer bug, and that we can improve fuzzing relying on reverse engineering techniques. In the end, rammer is still a problem, widespread, and it will be a serious problem for the next years, since a quick deployment of mitigation is not possible. Thank you for the attention, and if you want more details, check our paper, TRRespass, exploiting the many sides of target refresh.